pre-calculus students, welcome to section 11.2, vectors in space. Because vectors occur in our 3D world as forces, obviously. So we have a list of formulas that we're going to keep on the board while we're doing our examples. They are formulas you've seen before, only they were in 2 dimensions. And so we're just adding a 3rd dimensional component. So when you have a vector v now in component form, that would be written as v1, v2, v3, obviously. Writing that vector as the sum of unit vectors would be v1i plus v2j plus v3, and we use the letter k. To find the magnitude of vector v in 3 dimensions, v1 squared plus v2 squared plus v3 squared, take the square root, will be the magnitude. To find a vector in 3 dimensions with the magnitude of 1 called a unit vector, we will just take each of the 3 components and divide by the magnitude of v. That will be a unit vector. The dot product of 2 vectors in 3 dimensions, u and v, would be u1 times v1 plus u2 times v2 plus u3 times v3. To find the angle between those 2 vectors in 3 space would be u dot v divided by the magnitude of u times the magnitude of v. This would be the angle between the vectors in degrees. We usually give it. So let's use our formulas and do some examples. I chose number 10 from the book. Given an initial point of -735 and a terminal point of 0, 0, 2, find the component vector. So that would be vector v would be terminal minus initial. 0 minus a -7 is 0 plus 7. 0 minus 3 and 2 minus 5. Again, remembering that it is always terminal minus initial. To find the magnitude of the vector, that would be v1 squared plus v2 squared plus v3 squared. Add them up and take the square root. So this would give us, let's see, this is like 50 plus 20 minus 3. So square root is 67. Or as a decimal, right? And then to write the vector v as a unit vector in the same direction would be 7 divided by the square root of 67, -3 divided by the square root of 67, and -3 divided by the square root of 67. You are welcome to rationalize that if you wish. I don't feel the need to do that. Let's take a look at number 32. Find u dot v given these vectors u and v in 3 space. That would simply be u1 times v1 plus u2 times v2 plus u3 times v3. And then we would just add those up and get 28. Right, 16 and 12. Excellent. That would be the dot. Number 36, find the angle between these 2 vectors given u and v. So that would be inverse cosine of the dot product of u times v in the numerator. So this would be -1 times 1, -1 plus 3 times 2 plus 0. Obviously, that adds up to 5. I'm going to erase and put a 5. Divided by the magnitude of those 2 vectors being multiplied. So let's see. That would be 1 squared plus 3 squared plus 0 squared. Add them up and take the square root. So that will be the square root of 10 for the magnitude of vector u. For vector v, that would be 1 squared plus 2 squared plus -1 squared. Add up, take the square root. So that would be 4, 5, 6, the square root of 6. All right, going to grab my calculator. Make sure I'm in degree mode. I am. And I'm going to do inverse cosine of 5 over, I'll just put in the square root of 60 into the denominator. And that angle is 49.8 degrees. Excellent. Problem number 44. Given the two vectors, I wrote them as the sum of u and the sum of unit vectors. Are u and v orthogonal, meaning perpendicular, parallel, or neither? So how would we do that? Well, orthogonal, again, is when the dot product is 0, right? So let's put that. We're looking for where the dot product is 0. Let's see if that happens, right? So that would be -1 times 8, -8, plus 1/2 times -4 is -2, plus -1 times 8, -8. Obviously not 0, since this comes out to be negative. How do you know these vectors are parallel? When you have, when they're in 3 space, right? In 2 space, that was kind of easy. You just needed their slope, right? y2 minus y1, x2 minus x1 to be equal to each other, right? And that was easy because it was really just y over x, v2 over v1, u2 over u1, right? Because in component form, these vectors start at 0, 0. Well, these vectors start at 0, 0, 0. So how do you do the slope formula when you have 3 dimensions? So really what's going on here then, in 3 space, 2 vectors will be parallel if they go in the same direction, but their magnitudes are the same or different. So if these 2 vectors were in the same direction and they had the same magnitude, they would be equal vectors. It would be easy to see that they're parallel to each other. So what I need to know is, are they actually vectors in the same direction, but they are just different magnitudes? And here's what I mean. Notice that this first vector, right, u, is -1, 1/2, and -1 in component form. And vector v is 8, -4, and 8. So let's take a look here. What could I multiply -1 by to get 8? Would that same value, if I multiply 1/2 by that value, would it give me -4 and -1 to 8? So let's take a look. Vector u, if I multiplied, let's see, -1 times -8 would give me 8. Let's take a look. So what if I took vector u and multiplied it by -8? In other words, -8 times -1, 1/2, and -1. What do we get? That would equal 8, -4, and 8. Notice that that equals vector v, right? So if I take vector u and multiply it by -8, it does give me vector v, meaning that these vectors actually are parallel to each other. Now, because we're multiplying vector u by -8, vector u is going in an opposite direction, but they are still then parallel to each other, right? So if you have vectors that are going in opposite directions by 180 degrees, they are still parallel. They're not equivalent as far as magnitude or direction, but they are parallel. So these 2 vectors are parallel because I can write one vector as a multiple of the other. So I hope you have a great day, and we have one section left to cover in chapter 11, 11.3, of course.